As you begin page 3, keep in mind that the goal is to really start to become a bit more formal about our vocabulary of sequences, namely words like arithmetic, geometric, and quadratic, and to start using their equations. You can tell in number 28 and 29 on this page that we're going to start using more notation, like T of n, and the structure of these arithmetic and geometric equations. So on this page, it's kind of a prerequisite to have felt like you understood the Desmos activity, and specifically the nature of the blue cards in the Desmos activity. If you need to go back to some of your observations and really make sure that you shore up your answers to numbers 21 and 22 parts B, it may be a good idea to do so, because the equations and why the equation is written the way it is going to make a big difference in understanding what you're doing on this next page. So as you start number 27, which this video will walk you through, consider first what makes a sequence arithmetic versus what makes a sequence geometric in the first place. A geometric sequence in letter A is one that multiplies. So give yourself a little bit of time, if you can, to think about the sequence of numbers that would have a 64, and then another term, another term, another term, and then a 1/4. Think about all the possible ways you can get from a 64 to 1/4. Think about the fact that the numbers must be getting smaller as you go. So think about what types of patterns might work, but then limit your thoughts to only those that are geometric in nature, specifically patterns that are either multiplying or dividing. I'll give you a bit of think time, which means that there's going to be some awkward silence in this video, but I want you to take a few seconds to legitimately think before I just blurt out what the pattern is. I'll give you some time to think for yourself, maybe about 30 seconds, which again is going to be an awkward 30-second pause. The video will not stop, I promise. I'm just going to pause for 30 seconds. See if you can give yourself about 30 seconds to come up with a pattern that connects these numbers. Isn't 30 seconds just delightfully awkward when you're watching a video? Hopefully, though, you really did take enough time to think and find a pattern here, because there really is a pattern to this. And if you picked up on it, hopefully you found that to get from a 64 to a 1/4, you would have to divide, specifically divide by 4. 64 divided by 4 would be 16. 16 divided by 4 would be 4. 4 divided by 4 would be 1, and 1 divided by 4 is 1/4. So we know the pattern is dividing by 4. Now, on the Desmos activity, you hopefully notice that when patterns have a division, they're not only called geometric, but their actual multiplier ends up looking like a fraction. And I know that might seem kind of strange, because we're not really dealing with too many fractional values here. But when you're dividing, we actually say that the multiplier is going to be a fractional value of 1/4. It does kind of make sense when you think about the numbers that go past 1/4 if you continue the pattern further. For example, if the next number after 1/4 needed to be found, then 1/4 times 1/4 would be 1/16. And 1/16 times 1/4 would be 1/64. So you can definitely tell when you have numbers that are fractional why showing the multiplier as a fraction actually makes sense, because it's like you're multiplying by 1 on top and you're multiplying by 4 on the bottom. And then you're multiplying another 1 on top and another 4 on the bottom, and so on and so forth. So as you're thinking about the significance of writing a multiplier as a fraction, hopefully it does kind of hold up. Now, if you do think about it for some of the earlier numbers, the integer numbers, it actually does kind of make sense in that context as well. For example, 64 as a fraction is 64 over 1. And if I multiply by 1/4, then you can tell, because of the rules of fractions, 4 goes into 64 16 times, and that, of course, is our next term. So the long story short is when you have a dividing pattern, still consider calling it multiplication and just call it multiplication of a fraction. Now, on the previous page, one of the things you hopefully noticed about a geometric equation is the structure of it. All geometric equations generally have the same structure, and it may be worth making a note to yourself of this, just so you have something formal that you can go on once you kind of need to think about this in the big picture. If you want to consider even having some notes for yourself, this might be a good time to find some sort of piece of paper. Usually I would say it's the front page of the packet. And if you have access to a printer, you can always print the pages of the packet and print that front page as a note source. But even just a scratch piece of paper or a post-it might be a good idea, because generally speaking, all geometric sequences are going to have the same structure, and this might be a good time to make that official. Again, I'm trying hopefully to piggyback on some of the observations that you would have made on the previous page, specifically in question number 22, which is where we made some observations on our cards. But this hopefully was an observation that you recorded, or you can go back and record now that I'm explaining it in more detail. A geometric equation always has the following structure. T of n equals is pretty much traditional sequence notation. We'll talk eventually in a subsequent video about why we choose the letters T of n and n to be our variables, but for now just kind of roll with it. T of n is always going to be equal to a number times a multiplier to the power of n. So just to make sure it's absolutely clear what exactly goes into each of these parts of the structure, I'll be a bit more specific. The number that is outside of the parentheses, in other words, the number that is multiplying the base of this exponential expression, should always be your initial value. The initial value, again, is hopefully something that you made some observations about on the previous page in number 25. Yeah, number 25. Because the initial value is generally where the pattern starts. So that starter number, we were calling it. The number inside of the parentheses in a geometric expression is the number we've been calling the multiplier. Now, the order of these numbers is actually kind of important, simply because the multiplier is the one that needs to be raised to the power of n. If you actually go back and look at all of the cards in the Desmos activity, you'll remember that all of their multipliers ended up appearing in this parentheses. And hopefully that was an observation that you yourself also made. So in terms of writing your own geometric equation, you can tell that there are really two important numbers that you need to be prepared to identify. You need to be prepared to identify the initial value, because that number is the first number in the equation, kind of kickstarts the whole pattern. And then you'll need to be able to identify that multiplier. The multiplier number, again, is something that you can generally figure out, probably with just mental math, but is something that you do need to be able to write as an official value. So, as we go back to our example, and I'll keep my notes visible here so I have a bit of structure, let's see if we can make these connections. We've already discussed in letter A the multiplier, which is 1/4, so we know that that number is going to be inside of these parentheses to the power of n. The initial value we haven't yet identified, because if you notice, it actually labels for us the initial value in these little blank spaces. It's a little confusing at first, this idea of the initial value when you're looking at a list of numbers, and hopefully that was another observation you made on the previous page. When you're looking at a list of numbers, the initial value is always the number before the first term in the list. 64 was literally the first term that they gave us. 16 then logically would be considered the second term in the sequence. 4 would be the third term, 1 would be the fourth term, 1/4 would be the fifth term, and so on and so forth. But if you think about that pattern, first, second, third, fourth, fifth, it naturally stands to reason that the initial value, if it's the term before the first term, must be, and this is where you're going to have to bear with me here because the grammar of this is going to sound a little strange, the 0th term. And I'm sure there is much grammatical debate about whether it's the 0th or the 0th term, but grammar aside, the concept of there being a term before the first term is actually really important. Because when you're looking at a list of numbers, the initial value is going to be the term before the first one. It's a little strange. Bear with me on that. We'll get used to it as we use more sequences. But for now, let's just make an inference. If the pattern really does hold up, then it stands to reason that if I go backwards, I could predict what term came before 64. If to get 64, I must have divided something by 4, because that was how I got all these other numbers in the pattern, then logically, I must have divided something by 4, gotten 64, and I can think almost in reverse. That must mean that 64 times 4 could allow me to go backwards. The times 4 pattern going backwards seems to be true. 1 times 4 is 4, 4 times 4 is 16, 16 times 4 is 64. So naturally then 64 times 4, which is 256, must have been my initial value. In other words, it must have been the 0 term before the 64. So if I use this structure for a geometric pattern, then I can kind of copy this structure and fill in the relevant numbers as I go. The equation for this geometric sequence will be T of n equals, and again, bear with that notation for now. We'll explain it eventually, but right now maybe just get used to writing it. The initial value we said was going to be 256 times, because it's got a multiplier, 1/4 to the power of n. So again, notice the similarities in the structure from what I wrote in my sort of general formula versus what I wrote as my answer. 256 goes in the place of the initial, then parentheses, multiplier of 1/4, power of n. Now, in order to kind of keep things consistent, my suggestion is in this interim space between videos to try and make sense of letter A, make sure you're good there, and then try letter C. In the next video, we'll talk about something arithmetic, but for now, let's just chew on the idea of geometric and feel like we're okay there. So in between this video ending and the next one starting, finish letter A, finish letter C, and use the key in the learning plan to check your answer for letter C. Once you have the idea of a geometric sequence, we'll go back and look at arithmetic sequences separately.